Good morning. I'm Gustavo Elías. I'm agronomics coordinator in AYA. Some minutes after 9 o'clock, I welcome you to this plenary meeting, Sustainability and Efficiency, Technologies to Reduce Greenhouse, greenhouse gases emissions and using nitrogen efficiency. You can ask questions, writing them in the right section of your screen. And once the presentation is over, I will pass the questions over to the speakers. So please try to start asking questions during the presentation. In the top part of the website, there is a menu with a section entitled attendees. You will be able to contact speakers, chat with them, and arrange meetings with them. Also, we invite you to visit Aapresid space in the commercial hall. I will introduce Frank Brentrup to start his presentation. Frank, he has a PhD in agricultural science from the Hanover University. His thesis was environmental impact in crop production. He joined YARA since 1996. He's part of the business unit Food Chain and Global Solution. I will give the floor to Frank. You're welcome, Frank.
Thank you very much, Gustavo, and good morning and welcome to the presentation about nitrogen management for sustainable crop production. And the content of the presentation is split in two parts. The first is about nitrogen use efficiency as an indicator for sustainable N management and some issues that are related to that. And then the second part is on climate change, which is a future challenge for agriculture and obviously for all of us. And I will come to some points related to that during the second part. So let's start with nitrogen use efficiency, an indicator for sustainable nitrogen management. And I would like to start with a very basic description of what we mean with nitrogen use efficiency, because it can be defined in different ways. But in our context, we define nitrogen use efficiency as the percentage of the nitrogen applied that is removed with the harvested crop. So application of nitrogen to crops as mineral fertilizer, as organic nitrogen, but also, for example, as biological N fixation is on the input side. And then we have the removal of nitrogen with a crop that can be, or that's usually the main crop, so the grain, for example, but can also be straw if it is removed from the field. So everything that leaves the field is removed. In general, we can say the higher the nitrogen use efficiency, the better for the grower and for the environment, but you will see it's a bit more complicated than that. So in Europe, there's a group of mainly scientists, but it also includes some participants from the industry and from the policy that is called the European Nitrogen Expert Panel. And in this group, nitrogen use efficiency has been defined and has been is seen as a very important indicator for efficient and sustainable nitrogen fertilizer management. And the European N expert panel thinks this is important because the fertilizer rate alone is no criterion for the efficiency. If you have a high fertilizer rate that produces a high yield and a high removal, this can be as efficient as a low rate producing a low yield. So from their point of view, growers should not be limited by a simple ceiling of nitrogen input. Growers should aim at optimizing the balance between the input and the output instead of just simply reducing the input. And in order to evaluate nitrogen management properly, it should take 3 different dimensions into account. First of all, the nitrogen output as the percentage of the input. So that's the NUE indicator that I have described before. That's clearly an efficiency indicator. Then there should be a yield target. So a certain yield should be aimed at, should be the objective of the farmer. And this can also be expressed in the nitrogen yield. So that's the productivity dimension. And then last but not least, there's the environmental dimension, and that can be seen or can be illustrated by the nitrogen surplus. So the amount, the absolute amount of nitrogen that has been applied but not taken up by the crop. So that's a potential for losses to the environment. Let's see how the nitrogen panel has converted this concept, these ideas into a graphic, into a illustration, basically. So on this graph, you can see on the y-axis the nitrogen output in kilogram N per hectare and year. And on the x-axis, you can see the nitrogen input. And just by simply having these two values, we can calculate the nitrogen use efficiency, so the ratio of the output over the input. And there are 2 lines drawn in this graph. You can see a lower line, which is the border of the blue part on the bottom of the graph. That's the line that shows the nitrogen use efficiency of 50%. And 50% means that half of the nitrogen that has been applied is taken up and removed with a harvest, but half of it stays in the field and is in principle available for losses, for example, to the water or to the air. And that's a very low end use efficiency. And then the upper line is the 90% line, and that's a very high. That means that almost all of the nitrogen that has been applied is also removed with the harvest. So what is important to take into account is that there is also an upper limit of nitrogen use efficiency. If we remove more nitrogen from the soil than we apply, then this means that in the longer run, we will mine the soil and the soil fertility will be reduced. So that's also not sustainable. It's as unsustainable as applying more than needed. So we need to be somewhere in between these 2 values. But as I have said before, there are more dimensions, and one is, of course, the productivity. And in this graph, we can also draw a line, and that's the horizontal line that you can see here, that shows the productivity level. So, for example, for a certain crop, we know that the yield should be, let's say, at 10 tons per hectare or 5 tons, and this can be converted into a nitrogen yield. So by knowing the nitrogen content of the crop, we can calculate how much nitrogen is 10 tons of maize grain, for example. And this can be the limit or the desired level of productivity, and this can also be shown in this graph. So that's the horizontal line. And then we have the third dimension that I already mentioned. It's the environmental impact. And here we talk about an absolute value, and that's the so-called nitrogen balance or nitrogen surplus, which is the difference between nitrogen input and output. So the kilogram nitrogen that have been applied but are not removed with the grain and the harvest. So they stay still in the system. They are susceptible basically for losses to the different compartments of the environment, so water, air, or soil. And of course, for the nitrogen balance in some countries, like for example in Germany or other European countries, there is a limit for an nitrogen balance. So it should not exceed a certain value. And this is of course a challenge for the farmers. And here, on this slide, I have converted all these more theoretical limits and values into something more practical, and it's the application of the NOE concept to winter wheat grown in Germany. And for example, for the productivity, I've used the average wheat yield in Germany converted into nitrogen. So using a typical value for nitrogen content in wheat grain. And that means that the average wheat yield is equivalent to 128 kilogram of nitrogen per hectare, shown by the horizontal dotted line. And then we have a limit for the nitrogen balance, which is 60 kilogram in Germany. And that's a legal limit that farmers have to comply with. And that means the lighter blue part gives the limit for the nitrogen balance. And then, of course, as I said, we should also apply enough nitrogen so that the soil fertility is maintained and is still for the next generations available. So that's to keep the soil really healthy and fertile. That means for the farmer, there is a relatively small area, a wide area, which we can call a kind of the desired space for nitrogen management. So his nitrogen management should find its place in this wide area, which is limited by regulations, limited by profitable yields, and limited also by soil fertility aspects. And that gives a challenge to the farmer. And the question is how to arrive at this corridor. So let's have a look where we are today in Europe in this example. And I mean, first of all, we can say the global nitrogen use efficiency is around 50%. So that's the global value, but of course it's a very rough average above all crops and countries and so on. If we look at the European Union with all its regulations and improvements in efficiency because of the policy mainly and also the economic conditions, then the average is a bit higher than the global average. It's above 60%, more than 60%. If we look into, for example, trials, well-managed trials where we have pure mineral fertilizing systems, where we have measurements and where everything is done perfectly, also plant protection and the application of other nutrients and all that, then we can reach values of more than 80% or even 90% in such a well-managed field trial. So the question is, how can we improve the average values towards the values that we see in trials? Very important is balanced nutrition. That means to apply all required nutrients to give the crop basically a chance to grow to its potential, to its full potential. So you can apply as much nitrogen as you like. If there's no sulfur, no phosphorus, not sufficient potassium, it will not grow, and the nitrogen use efficiency will be very low. So that means that balanced nutrition is very important. Then, of course, if we think of whole regions or systems, countries, and their NUE, then the use and application of organic fertilizer is very important, because organic fertilizers and animal manures, for example, are very important to be used as efficiently as possible, because they are difficult to manage. They release nutrients during times when they are not needed. Sometimes they can be very leaky during the application. They need to be incorporated. So there's a lot of improvement possible in the organic fertilizers. But when it comes to the mineral fertilizers, there are also differences between the forms of nitrogen, for example, and I will come back to that in a minute. And then, of course, it's important to look what is the real requirement of a crop, what is the growth of the crop, how is the season going, is there sufficient water, is the soil supply higher than normal, things like that. So it all goes into the direction of precision farming, where we measure the crop, where we use satellite images and in-season field measurements to adjust the fertilizer rates according to the real demands. Here you can see one reason for the differences between fertilizers, between different fertilizer types. So the reason why, for example, urea typically has a lower end-use efficiency than other nitrogen forms, like, for example, YARA or the nitrates in general, is that urea is very susceptible for ammonia losses. This is because urea reacts alkaline in the soil. It increases the pH around the granule after application, and this leads to a condition where the ratio between ammonia and ammonium is towards the ammonia, and ammonia is NH3, is very volatile, and it leads to gaseous losses of nitrogen from urea. And these measurements here are from Argentina, and you can see that under different conditions. So it's either urea incorporated and concentrated in a placement, or urea broadcasted, or the third system is a YARA system where we applied nitrates. And you can see that these losses can be as high as 40%, which means close to half of the nitrogen that has been applied is lost to the air and is deposited somewhere, maybe on a field, maybe on a forest, somewhere where it is not intended to be. And this, of course, has an impact on the nitrogen use efficiency when you compare urea with nitrates. However, the ammonia losses are not only important for the farmer. It's something that, for the farmer, a 40% loss is definitely very significant and very relevant, since it means that he has to apply more than he would have to apply with a nitrate, for example. But the losses have also consequences for the environment and also for human health. So ammonia losses in Europe, for example, are regulated by EU regulations on air pollutants, because they are important in the formation of particulate matter, of fine dust, or summer smog, how it is sometimes called. That has respiratory consequences for humans, so it's really a health issue. It is also impacting natural ecosystems by acidification and eutrophication of natural systems that usually are limited by nitrogen, and then they get some more nitrogen than they are used to. So other crops or other plants start growing, for example, that are not wanted. And we have to say that agriculture has a very large share in these emissions. It's mainly related to the animal husbandry, but also mineral fertilizers, and in particular urea, have a significant share in the ammonia emissions. So the other thing that is very important in order to increase the nitrogen use efficiency up to a level that is comparable to what I've shown for the trials, so 80-90%, is precision farming. So that means optimizing the nitrogen management during the crop cycle. And here we have different options to offer. Of course, things like at farm, so satellite images that can be converted into biomass maps, and that can be used to derive site-specific recommendations for nitrogen rates. This is one option that is available, but also N-Tester, which is a chlorophyll measurement system, a handheld instrument that you can see on the bottom left side in a picture, or also lab analysis, soil analysis during the season, where you can see whether there are deficiencies in certain nutrients that can lead to a limited nitrogen uptake because the crop growth doesn't work as it should be. This all leads then to a cropping solution based on the information from the different instruments that are then converted into recommendations for certain products and certain rates during the season, and according to the need of the crop at the different growth stages. And here you can see two examples for maize and cereals, where all this crop knowledge and the information from the different tools is converted into a cropping program and into a fertilizer recommendation. With this, I would like to come to the second part of the presentation, and this is about climate change and greenhouse gas emissions. And here, I would like to start with a very broad picture with the global emissions and the split of emissions to the different sources of the emissions. The data are a bit old already, so 2010, and need to be updated, but there is, at least from IPCC, not much available since then, but FAO, for example, offers data, and we are at the moment in the process to update this information, but to be honest, it hasn't changed a lot in the global picture, at least. So what we can see is that about 20 or 20 to 25%, depending on the reference, of the emissions are somehow related to agriculture and land use. And if we look a little bit more in detail into these emissions, then you can see that the pure agricultural part is about 10%. And there we have livestock and manure emissions from these sources. And we have mineral fertilizer, we have rice, paddy rice in particular, and also the cultivation of organic soils and the management of residues as the main sources. Then the second big part in this sector of land use and agriculture is the change of land cover, so mainly deforestation. So the change from forest to grassland or from grassland to arable land leads to a loss of carbon, and this is behind the 11.2% that you can see here. So we can see that agriculture has a significant share in the emissions, and that's why it is also part of the discussions around the Paris agreements and all these political contexts. So what do we do in a fertilizer company as YARA to measure and to address this issue of greenhouse gas emissions? Of course, we calculate the carbon footprint, the greenhouse gas emissions for our products. So that's the first thing we do. We have a certain boundary around this calculation. So we include all the raw materials, the energy that we need, the minerals from deposits that are mined, for example, and then of course the production in our factories. That's all included in such a calculation. But we also look further, so the use of our products up to the harvest of a crop. That's a different scope, basically. Both parts are important in the calculations, as you will see in the following. So when we look at a crop, the carbon footprint of a crop, for example, like maize or grain, then we can see that the emissions from the production of fertilizer as well as from the use of fertilizer are very important sources, which you can see on this graph here. And this graph shows the footprint of a ton of wheat, the kilogram of wheat grain, expressed in kilograms of CO2 equivalents. And then you can see that we have N2O from the soil. The green part, that's the use of the fertilizer, and the blue part is the production of mineral fertilizer, in particular of nitrogen fertilizer. So what can we do about this? Let's start with the production. We have invested in technologies to improve the energy efficiency in the fertilizer production, as well as in the emission control. So there is, and you will see that on the next slide, there is a certain part, especially in the nitrate production, in the production of nitrate fertilizers, that releases emissions that contribute to climate change, N2O, nitrous oxide. And in the past, these emissions were quite significant, and they are still significant in the production of nitrates outside Europe. So in Europe, due to also regulation and technical improvements, we have reduced these emissions of N2O by about 90%. And here you can just see some pictures from a nitric acid factory, and then there's the technology in the middle where a catalyst is installed to reduce the emissions. And then on the right-hand side, you can see that the emissions are removed from the chimney, basically. What does it mean in terms of the carbon footprint of the different fertilizers? And here we look at nitrates, and you can see on the left-hand side that the footprint, the greenhouse gas emissions per kilogram of nitrogen have been reduced from almost 9 kilogram to 3.3 kilogram on average in Europe. That means a huge improvement. And on the right-hand side, you can see that if we compare this with today's footprints of nitrates in other regions, like in Russia, North America, or China, that the European, and that means also the YARA production, has a much lower footprint thanks to these improvements. For our own products, we have calculated the carbon footprint per factory and per product. So we have a certified value available, which is not, let's say, published on the YARA website, but which is available on request. For example, if there's a customer that is particularly interested, or if there is a project that needs such information, we have that available. And we are in a continuous process of improving these calculations and also updating. The second important source of emissions in a cropping perspective, in a arable farming perspective, is the N2O emissions from the soil. And what is this about? So here we talk about two processes, about microbial processes in the soil that convert certain nitrogen compounds in the soil. And during this conversion processes of ammonium to nitrate and of nitrate to nitrogen gas, N2O appears as an intermediate product in these microbial processes, and N2O is also volatile and can be lost to the atmosphere, and is a strong greenhouse gas. Dependent on certain conditions. So, for example, the nitrification process depends, of course, on the availability of ammonium in the soil, and then there are certain microbes, bacteria that use the ammonium as an energy source and oxidize it to the nitrate form. And this is a very common process that happens in almost any soil, and that is a relatively quick process as well. So that even if urea is applied or ammonium fertilizers, they are normally nitrified to nitrate, which is then taken up by the crops. The denitrification, in contrast, is a process that depends on anaerobic conditions. So if there is not sufficient oxygen in the soil available for the microbes, a certain group of them is able to switch to nitrate as a replacement. N2O as an intermediate product, and can lead to some peaks in N2O emissions, for example, under these waterlogging conditions, or if there is a very heavy soil together with a lot of rain, that can have consequences in terms of N2O emissions. On average, the two processes are estimated to lead to about 1% of N2O nitrogen per unit of nitrogen applied, but this is very variable. Under aerobic conditions, so that means if we have a well-managed arable soil where there is no oxygen deficiency in the soil, then normally the emissions are generally low. And we can also observe that the emissions from ammonium or urea sources are higher than from nitrates. If, for example, a grassland has a heavy soil and is wet and not well drained, then of course it can be the other way around. So in that case, nitrates lead to higher emissions than ammonium or urea. So it's really depending on the conditions which nitrogen form is the better in terms of N2O emissions. Generally, we recommend we should again look at the nitrogen use efficiency in order to reduce the N2O emissions, because what we can say is that any nitrogen that is taken up by the crop is safe in terms of emissions. Whether this is ammonia or N2O emissions or leaching, doesn't matter. If it's taken up by the crop, it's safe, and it has, we can say it has reached its where it should be, basically. And the second, of course, the second recommendation is to use climate-friendly nitrogen fertilizers based on the best available technology. So here you can see an example where we have compared different practices in maize and in coffee, and we can see in the standard practice, which is the common practice basically in the country, that we have a higher carbon footprint because of, first of all, not using the best available technology products, but also having a lower end-use efficiency, and the, let's say, range of improvements for the maize, 20 to 30% reduction with improved practices, and in coffee we had on average 16%. So it's a significant enabler for reducing the greenhouse gas emissions. We have done similar studies using the Cool Farm tool, which is a farm greenhouse gas calculation tool in maize in Argentina, and we found very similar reduction potentials. So between 20 and 30% for maize, if we replace the traditional fertilizer practice with an improved practice, higher nitrogen use efficiency, production with a better emission control. So this confirms very much what we found in the other crops and the other regions. And with this, I would like to conclude the presentation. And the conclusions, the main conclusions are that if we choose more efficient nitrogen sources, this means that we can increase the kilogram of grain that we harvest per kilogram of nitrogen applied. And that means application of nitrates. And if we talk about nitrates, we are talking about fertilizer that have at least 50% nitrogen, are more efficient than other nitrogen sources. And this is mainly because of the lower ammonia volatilization losses, but also quicker assimilation, for example, by the crops. So the nitrate is not bound to the clay particles, for example, as ammonium. Furthermore, balanced nutrition with all nutrients, split application, the use of precision farming tools to adjust the nitrogen rates according to the crop requirements, all that is important to increase nitrogen use efficiency. And increasing nitrogen use efficiency means that more harvested nitrogen in the crop ends up in the crop, and less nitrogen is available for polluting the environment. So that's why we in YARA develop crop nutrition solutions, which should increase the nitrogen use efficiency and reduce the environmental and climate impact, and should also give a good profit to the farmer. So regarding the last part of the presentation, we can say that we achieved already significant reductions in the greenhouse gas emissions, both in the fertilizer production and also in the field compared to other fertilizer forms. And but we know that there's further scope for improvement, and that's a main task of our research and development work in YARA. Thank you very much, and questions are welcome.
Muchas gracias, Frank.
Thank you very much, Frank. This has been a very clear presentation. This is the first question from the audience. Where can we access to the information on carbon footprint certificate? Could you give us more details?
You can either contact me directly, or let's say the official contact in YARA would be our central HESQ team in Oslo. So if you, in this case, I would recommend to send an email, for example, to me. But if you wouldn't know me, then such a request would be directed to the Central Health, Environment, Safety organization in Oslo, in our central office. I
Bien,
hope that.
muchas gracias.
Yeah.
Bien, muchas gracias. Agrego.
Thank you very much. I would like to add a comment as part of the Argentina YARA's team. You can contact any member of Argentina's team. We are going to refer to researchers or to whatever area is concerned with that. So there is available information. There is another question related to the fertilizer rates. Compared to Europe, in Argentina, we use smaller nitrogen fertilizers rates, both in wheat and corn, but we have high yields. Which could be the reason for that, for such a difference in the rate?
Yeah, I think maybe Gustavo is in a much better, he's much more experienced in that point. But what I know is, of course, that especially in corn and maize, you have a lot of soybean in your rotation, and of course the biological N fixation by the soybean is part of the nitrogen that is then supplied to the maize crop. So in a real nitrogen use efficiency calculation, this input through the soybean should also be accounted for. So it's in that case, my take would be that it's not only the mineral nitrogen fertilizer, it's also the fixation of nitrogen by the soybean crop. But maybe Gustavo can add on that. I think it's the same as with the soybean. If it's a legume, then definitely it provides nitrogen into the system. But even if it's not a legume, so we have also a lot of cover crops in Germany, for example, which save nitrogen after harvest through the winter, basically. So it's really the one of the reasons why it's grown. It's that it takes up nitrogen that is still in the soil after harvest and saves it or let's say prevents leaching losses. So cover crops is definitely a good measure. It also adds some carbon to the soil.
Bien, perfecto. Y
the next question is if fertilizing digging urea at planting, has it also an effect? When you dig,
sí, aplicar.
If applying urea at planting, does it also cause nitrogen loss?
Yes, of course. It depends if it's incorporated. The losses are usually a little bit reduced. But we have seen from the example from Argentina that even incorporated urea, if it's concentrated and in a band, in a placement, it can create also very high losses. It depends a bit. So in Europe, for example, we have I think it's a German legislation that farmers have to incorporate urea after application in order to reduce the ammonia losses. So that's really, really strict. But still, whether you apply at planting or later, it will create losses.